Hey everyone, so for this video, let's discuss the Newton-Raphson method, which is an open interval method similar to the fixed point iteration. Again, for open interval methods, we do not need to know the interval at which our solution lies, but instead we just want to have at least one initial guess, and then we will let the algorithm find the root itself. So for the next strategy or algorithm for open interval methods, we have the Newton-Raphson, which is the most widely used method for finding roots of nonlinear algebraic equations. And if you would ask now, your calculators are probably utilizing this method or a small or a variant of this method. So the good thing about Newton-Raphson is that it is self-starting, meaning it will go on over the next root similar to the fixed point iteration, you know. And then it can also be used for finding complex roots, you know. Although we will not discuss complex roots here, but thing to know that we can also utilize this for complex roots. So how do we find the root or approximate root using Newton-Raphson method? How do we define this? So using the Taylor polynomials, no? If you can remember the Taylor series, we have this series, and if we want to equate this Taylor series expansion into zero, and then truncate this Taylor expansion, okay, into its two terms, we can find the iteration function, which is this, ano? So what does this mean? So n plus 1 basically means the present approximation, and n is just the previous. Okay? So take note of this equation, which will be the algorithm used for the Newton-Raphson. Now, how do we represent this visually? So let's say we have an initial guess, which is this, and our function, let's say, I think this is a parabolic function. The first thing that we do in Newton-Raphson method is we find the tangent line of this function at this point. And then this intersection with the x-axis, wherein f of x is equal to 0, basically, is now the new solution, which will be this actually in our curve. Now, we will do this iteratively, meaning we will repeat this root finding algorithm, and then it will approach to this root here. So if you do this continually, we will arrive at this root here. So now, what's the next step? Or sorry, what is the algorithm itself? So we have the algorithm here. Okay, I will just make things simpler. We have two conditions for finding the roots here. We want to see if the derivative of the function is 0. Okay, then it might diverge, no? Or it might not be a solution because it will be in you call this undefined, ano? And if your f of x is equal to 0, it will be the solution. And if your stopping criterion is met, then it will be your solution as well. Sige, let's just do this anyways. No, I think this is a little bit confusing. This is for the implementation using your computers, no? Let's just do this example. So another thing to take note pala, no? I did not discuss this. So this method will converge or will arrive at a solution if our root is near, no? Or if our initial guess is near that true solution. So it might diverge if the initial guess is further away from the function. Or sometimes, no, again, if the first derivative of this function is 0, you know, because again, if the derivative is 0 here, then we have 1 over 0 scheme, therefore this will diverge, no? So fx minus some very high number or very close to a high number it might diverge our solution. So let's say we have a given function. Let's say this is our function, and then we want to obtain a solution using the Newton-Raphson method. And let's see the first three iterations when using the initial guess as x of 0 is equal to 0. So how do we do this? So our iteration function will be in this format wherein we substitute the value, sorry, not substitute here, we substitute the function of f here, which is this, basically. And then we find the derivative of this function. So the derivative of this function is, so 3 cosine, and then negative e raised to negative x as your denominator. So you want to find the derivative of your function for this Newton-Raphson scheme. And then after doing this, you will arrive at this solutions for the first three iterations. Okay? So let's do this actually in an example. So approximate the value of x until the relative approximate error or the percentage approximate error is equal to 0.01%. If f of x is equal to arctangent 2x squared minus 1 when the initial guess is 1.5. So how do we do this, guys? So again, our iteration function for the iteration scheme, we have x sub n plus 1 is equal to x sub n minus f of x sub n over the derivative of f of x sub n. So the f of x here, guys, is already this function. Okay? So this will be equal to x sub n minus arctangent, arctangent 2x squared minus 1. So this is your numerator, your function. Okay? For the derivative, you want to find the derivative of arctangent. Okay, so what is now the derivative of arctangent? If you can remember the derivative of arctangent, so let's show this using this. We have arctangent u is equal to 1 over 1 plus u squared, diba? You can remember, multiplied by du using the chain rule. So the answer should be, we have 1 over 1 plus the square of 2x squared, okay, multiplied by the derivative of 2x squared using the chain rule, which is 4x. Okay, so simplifying this, we have x sub n minus, we have arctan 2x squared minus 1 over 4x over 1 plus. So squaring this for both of the factors, we have 4x to the 4th power. So now this will be our iteration scheme. And we can solve this using the iteration table. No? So we have iteration, we have the x, and then we have the percentage relative error or percentage approximate error. So the iteration here is from 0. So the initial guess here, guys, is 1.5. So you'll input here 1.5. So we do not have yet previous, so no relative error. And then we can now solve for the first iteration. So the first iteration here using our calculator. So for our calculator, you just utilize one variable for the iteration scheme. So we have x minus arctangent. So arctangent here, shift tan. So be careful, no? Be mindful to always change your calculators into radians. So change this first into radians. And then 2x squared minus 1 all over, we have 4x over 1 plus 4 alpha x to the 4th power. So calculate this for the first iteration. So the initial guess is 1.5. So the next guess will be 0.2529. So this will be 0.2529. So the approximate error here, again, I will not write this anymore. So we have the present minus the previous over the present times 100. So use the calculator scheme. So the present here is 0.2529. The previous is 1.5. So the absolute value of this is 493. 493.1198%. So this is a very large number. For the next iteration, we will now substitute again this value to our iteration function, 0.2529. So this will be 1.1298, no? For the second iteration, and then get the relative approximate error. The approximate error is 1.1298, and we have 0.2529. So this will be 77.6155%. And then for the third iteration, so we haven't reached the where's the calculator? Oh, it's gone. So let's okay, you have to do this again. Sorry. So the calculator crashed. Let's do it again. Tangent 2x squared. Okay, in radians. So the radians minus 1. Now we have 4x over 1 plus 4 alpha x to the fourth power. Okay, so calc, we have 1.1298. Okay, so it became 0.8014. So the relative error, we have again present, previous, present times 100. So calc function, this will be, the present is 0.8014. The previous is 1.1298. So we have 40%. So 40 0.9783%. So for the next iteration scheme, again, let's do this again. So calc 0.8014. So 0.8764. Okay, and then calculate the relative error. So calc the present is now 0.8764. The previous is 0.8014. So we're getting closer and closer. So this is a smaller number, 8.5577%. And then calc, to back again, calc 0.8764. So we have 0.8824. And then for the approximate or the relative error or the percentage relative error, percentage approximate error, yeah. Okay, we have a 0.8824 and then 0.8764. So, sorry, where is it? Oh, so we did not, okay, dito pala. 0.87, sorry, 8824, then 0.8764. So 0.68%, no? And then I guess this will be the last one. So this will be substituted again. So calc 0.8824, our previous approximation. So this will be the same again, no? So as you can see here, this will be 8824 again. Therefore, if there is no difference, then the relative error, the percentage relative error will be 0%. Therefore, this is less than or equal to 0.01%. Therefore, the criteria or the stopping criterion is met. Therefore, the final answer or the approximate error that we found was 0.8824. Okay, so that will be all for Newton-Raphson method. So thank you guys.